Okay, so let's go through the middle portion of chapter 30. Right, and again, this chapter is induction and inductance. And so we're just going to focus on chapter 30, sections 5 through 8. And so we're going to start off with 30.5. Induction and energy transfer. Okay, and so let's just kind of recap what we talked about in the last video. And so let's see, we had magnetic flux, and so we have the special case of B is constant and B is parallel to A, which, as a reminder, that means perpendicular to the surface. And in that special case, we just have the magnetic flux as B times A. Right, but in general, if B is a constant, then we can also just write B A cosine theta, right? And so, we have this general form that's always true, and then we kind of have this special cases where life gets a little easier, right? In general, for this class, this is about the trickiest you'll have to actually do. Okay. Let's see. Then we had Faraday's law. We'll say with many loops, there we go. And then we had Lenz's law. So an induced current will always oppose its creator. Right, and so if it's a changing magnetic field that gets to make this change in flux, then what you're going to do is the induced current based on this potential is always going to try to make a magnetic field to oppose the change, right? So whatever change you have, the induced current will always work to oppose that. Okay. Yeah, and so let's start with an example or a little situation. We have a magnetic field, right? This would be going into the board. Okay, and give that a nice little label. And then we have a rectangle of wire. That we are going to take and we're going to pull it out. And so this would be some external force. right? A textbook draws a hand grabbing it. I'm not going to attempt to draw a hand. Yeah, and that's that. And so we could say we have some velocity going this way. We can go ahead and say this loop has some length. Some, I guess, also. Right. Our external magnetic field is confined. Such that we can use the variable x. Right, I did a kind of squiggly x, so it's very clearly different from the magnetic field x's. Okay. And so then let's see. If this is going to be leaving the magnetic field, we're going to be decreasing the flux through it going into the page. All right, so let's write this down. As the loop leaves the field, the area through which we have flux decreases. The induced EMF will create a current that increases the flux into the page. Okay. And so by right-hand rule, we can say it's going to be a clockwise current. Cool. Okay. So that's fun. So let's see. So the rate at which you do work is power. And so we can say for this, power is equal to the force times the velocity, magnitudes of everything. We said this already. As A decreases, the flux decreases. Everything's perpendicular, so we can say phi sub B is equal to BA. Okay. Which we can say is equal to the magnitude of the magnetic field. And then the area we have is going to be L times X, right? And as we pull more and more out, our X value is going to decrease, is kind of what we're working with. So as BLX is going to be phi, our flux, and we can kind of put a note here and say that we're allowed to do this because everything's perpendicular, right? And B is constant. Okay. And then if we want, we can look at the magnitude of the EMF, and we get right, we just dropped there's typically a minus sign in Faraday's law, right? There's one loop, so N is 1. We're looking at the magnitude, so we're just going to ignore that for now. Okay, so if it's the time derivative of the flux, and we have an expression for the flux here, we can say it's d by dt of BLX. Okay. And so B and L are both going to be constant. right? The height of this isn't changing, and the uniform magnetic field's a constant. And so it's not the prettiest X. There we go. Okay. And so we have dx dt, which, as we all remember, is equal to v. And so we have BLV is going to be the magnitude of the EMF. And so I'm just going to cut out all the work that's in there. And we have this lovely result. Okay. But let's see. Ohm's law tells us this. The EMF is equal to I times R. And so if we want, we can solve for the current. Okay, and we can go ahead and plug this in. Okay. And so again, we're just gonna put that result off to the side. And we'll come back to that in a second. And so now something we want to kind of think about is, okay, so if our current's going this way through here, it has to be going that way there, this way here. Okay, now we have current carrying wires in an external magnetic field, and so they're going to experience a force, right? And so let's see. If we right-hand rule this, right, if our current is going up, that's going to be V. B is going into the page, and so we get, we'll call this F1. Okay. Same line of reasoning, make that F2. This side is not in the magnetic field, so we have no force there. And we will call this F3. And so we know that the force is equal to IL cross B. And then we can kind of say, well, this leg and this leg of the loop, they're going to have the same length, so L is going to be a constant. Well, different L, I guess. So we will go ahead and we'll make this a lowercase l. Yeah, so these are both going to have some length L. They're going to have the same current because it's the same loop, same magnetic field. And so we can say F2 plus F3 equals 0. All right, and then we can have our L1 here, which was just our capital L value. And so then we can say, overall we can say, the sum of the forces, some of the Lorentz forces, right, from a charged particle moving in a magnetic field is just equal to F1, which is equal to ILB. All right, and we can go back to the capital L since this length and this length are the same. Okay. Okay. So we have... Oh, I lied here. This is an I. This is the current. Okay. So we can go ahead and we can plug in... I guess we'll call this equation 1. And so we can plug that in for this current here. And so we can say the force is equal to BLV over R times LB, okay, which gives us B squared L squared V over R. Okay. And so what we get from this is the net force on this wire is B squared L squared V over R. Right? And since we have it not accelerating, that's also the magnitude of F external, right? The net force has to be 0. And so the Lorentz force is going to balance this force if we're going at a constant velocity, V. And so we get this as our force. But we did say power, the rate at which work is done is equal to force times velocity. And so if we multiply this expression for force times the velocity, we get power is B squared L squared V squared over R, which I'm going to rewrite as terrible. BLV squared over R. Okay. Yeah. And so this is the rate at which we do work. Okay, but if we are moving currents through a wire, we discussed how that makes the wires heat up a bit. I think most recently we saw that when I was playing with the big solenoid. I was picking up all the nails. At some point I was like, oh, hey, this is getting hot, I gotta put it down, right? Because we were running a lot of current through there in order to make a big magnetic field. And so this is still going to be true. We're still going to have some kind of thermal energy, which we said P is equal to I squared R, back when we were talking about circuitry a little bit. And so if we have an expression for I, right here, okay, so it's BLV over R, right, BLV over R, all that squared, right, because it's I squared, times R, which gives us BLV squared over R. And look at that. We got the exact same result from two pretty different arguments. Right? We did power is force times velocity, and we did power is I squared R, and we get the same result. And so that should be comforting. Right? If we were looking for the same thing in a couple different ways and we got different results, then, you know, something's not good. Okay. Okay, and so that's 35. Let's go to 30-6. Induced E fields. Okay, so let me figure out how we're going to draw all this. So we have, what do we have? Let's start with this. We have some region where there's an external magnetic field. You know what? Aha. Oh, well. Let's get another one. I think we need 4 of these total. There we go. Technology. Okay. And so, for the first part, we're going to say we have a conducting ring in the middle. Alright, it's copper. I'll see you. Okay. And so, let's see. We're going to go ahead and call this distance R. This is little r. Magnetic field B. Okay. And so let's have B increases at a steady rate. Okay, and so the magnetic field is going into the board, as we can see. And so if it's going to increase, we are going to want an EMF that induces a current to come out of the board. And so if we right-hand rule that, we are going to want a current that goes this way. All right. Or we can say we get an EMF that goes that way. Right. Just going from high to low potential. Okay. Well, if we were to do the same experiment, but we don't have that copper ring, right? So now what I'm going to do is, we'll call this A, B, C, and D. All right, so in A we had a conducting ring, and we're all fine and good that, yes, changing the magnetic flux through this ring is going to necessarily make a current. Just like we saw in class when I was playing with those galvanometers and I had different coils, I was moving the magnet, you could see that you do get current and potential, and all these things. And so now what if the copper ring isn't there anymore? What if we just have some arbitrary circular path to look at? Right? What's terrible circle? Right, it's alright, we'll call it better. Right, and so now we're going to look at a circular path, also of radius little r. This is still big R. And we're going to try to see what's going on here. Think of a color. Well, so if the ring is removed, we still expect to get some kind of induced electrical field here. Right, the fact that there was like a loop of a ring through which there was flux, like a lot of that just works to illustrate like the magnitude of the EMF you're gonna get, but in reality, you're still gonna have an electric field, even if you don't have a conductor through which you're changing flux, right? So we still have a circular path here. We're still changing the flux through that circle, and so we still expect to get some kind of an EMF, right? And so now we're going to say our electric field points in this direction, just like we could have done here, right? If the potential is going this way, right, from positive to negative, right, and so we have a current going this way, we can argue that, okay, in order for that current to travel and for that potential to exist, we need an electric field, right? We saw in the last unit the having a potential and having an electric field are roughly, they go hand in hand. I was gonna say they're the same thing, but they're not the same. But like one requires the other. Right? They're two sides of the same coin. And so if we just have an arbitrary circular path that isn't a conductor, right? We still change the flux through it. We still make an electric field that goes around in a circle. And so, well, now let's stop pretending that we're looking at a specific loop, right? We can argue that if we are still steadily increasing B in this regime, then we're going to have electric fields going like this. Okay? And we could even argue, if you're outside that region where the magnetic field is increasing, well, you're still changing the flux through a circle in that area. And so you still get an electric field outside, right? And now, obviously, you can reason that, you know, the bigger we make this, the weaker the electric field is going to be further and further away. But we're still going to have some field lines there. Okay. And so the main idea here is a changing magnetic field produces an electric field, right? And so that's kind of how this is all working out. You know, we didn't really have an explanation for why the change of flux through a loop induces a current. We kind of just said, well, it happens. And the reason it happens is because that changing magnetic field or the changing flux, it produces an electric field. Okay. And so yeah, what we can do is, let me zoom in on this a little bit. Let's say we are going to kind of have that same picture. I'll get a little smaller. Nope, that one's bad. Who needs it? Okay. Right, same picture as in C. Now we're just kind of zoomed in a bit so we can see things clearly. And we're going to draw 4 arbitrary paths. We'll call that 1. Over here, we'll have path 2, path 3, and then path 4, right? And they're just kind of arbitrary blobs. You know, we'll say these are identical arbitrary blobs. Okay. And so, if we wanted to find, right, the important thing here is the area is a constant for all of these. A1 equals A2 equals A3 equals A4. And so if we wanted to find the EMFs around these, we would say, well, we have 1's equal to 1, shocker. 1 is equal to 2 because both of these loops here are entirely within the changing magnetic field. And so they get the entirety of the flux. And so those will be greater than E3 because this only has a small portion that's going to have a changing flux through it, right? Out here, nothing happens. And then 4, even though we still do get an electric field out here, if we look at this as the loop we're going through, none of it has a flux changing through it. And so the EMF around E4 is 0. Cool. And so that's all this section's trying to say. Okay, so now what we're gonna do is consider like a point charge traveling around this loop, right? So the work done for that must be, well, we know work is equal to EMF times charge. That was kind of how we got to the definition of potential. It's like the work per charge to hold something there. Right, where this is the induced EMF. That's a test charge. Okay. So let's see. We also have the definition of work as the integral of f dot ds. Well, let's see. If we argued this is going to be a constant electric field, we have F is equal to QE. We're going in a circle. So the integral ds is equal to S is equal to 2 pi r. Okay. And let's see, if we're traveling in the circle this way, well then F is always going to be in the same direction as E, the dot product goes away. And so we can say this is going to be Q naught for our test charge times E times 2 pi r. Get out of here. Okay. And so what are we gonna do there? So if we set these two equal to each other, epsilon naught Q naught is equal to Q naught E times 2 pi r. So we can cancel these out. And we get the EMF we induce is equal to 2 pi r times E. Okay. So that's good. And what do we get from that? And so if we take, I guess, this expression, we can rewrite it as work is equal to the path integral of f dot ds, which we can say, right, if we're just going to keep it general, right, f is equal to QE. We can pull out our Q naught for the test charge, times the path integral E dot ds. Right, and so we haven't actually really done anything. We just rewrote this in a general form. And so if we divide both sides by Q naught, we can get work over Q naught, which, oh wow, that's our EMF, is equal to the integral of E dot ds. Okay. And so, yeah, this is a result that I think is going to be interesting. And so let's remind ourselves what Faraday's law said. Right. And so we can set these two equal to each other, such that the integral of E dot ds is equal to the negative change in flux. And so this, we can say, is Faraday's law, just a bit more complete, right? And so what can we do with this? If we can know the change in flux, we know the path around which we're going, we can calculate the electric field we create by changing a magnetic field. And so let me write that down. Right, that's pretty cool. And so again, right, we started with this kind of picture of like, hey, if we do have a loop of wire and we can change the magnetic flux through it, well, we can make a current move, right? That's something that we could show in class, we could do a lot of work with. And now we're just saying, if you change the flux, you make an electric field, and this is how that's related. Did I say magnetic field? I meant electric field. If you change the magnetic flux, you make an electric field, right? Cool. Okay. What else can we do with this? Well, we have potential is equal to the integral E dot ds, right? That was something we talked about before. So let's say we're going to do this along a closed path. Well, we can say it's equal to EMF. And now it's a closed path, so we put that little circle on the integral sign. And we all agreed that this was equal negative d phi dt. Right, and keep in mind, I put EMF here because that's specifically for like a circuit or closed loop, right? Yeah, a circuit is a closed loop, but you know, there we go. Okay, and so we're kind of tying a bunch of things together here, and we'll get to work with those in class. Okay, and so we'll hop over to 30-7, inductors and inductance. Okay, and so inductor, when we talk about that in a circuit, it's just a little curly guy. Right, just like a capacitor was this, an inductor is that. Right, and like a solenoid is a type of inductor, right? Anytime you have like coiled up wire, you get something called inductance. And we actually have a definition for inductance. L is equal to N phi B over I, where this is the inductance magnetic flux current, and then of course we have the number of loops. Yeah, so here, let me kind of put that over to its side. Oh. Okay. Yeah, and this has units of 1 Henry 1H is equal to 1 Tesla meters squared per amp. Okay, and so let's look at the inductance of a solenoid. Okay. So, where are my notes? So let's say consider a long solenoid of cross-sectional area A, and we want to know what is the inductance per unit length, and then we're going to say near the middle. Right, that's where the magnetic field's constant, so that's where we're going to look, right? We're looking inside of it, you know? Okay. And so if we know we're changing, well, let's just look at the total, they call this the flux linkage. Right, and they call it that because we're linking together all the fluxes through all the loops. And so if we have N the number of turns per unit length, well, we're going to have to multiply that by L, which is some length we're looking at. And then that's going to be times BA, right? And so A, the cross-sectional area, B, the magnetic field. We said we're looking at it near the middle, right? So we have a constant uniform magnetic field that's going to be perpendicular to that surface. If it's perpendicular to the surface, it's parallel to the area vector. And so everything is working out for us. We know the magnitude of B. That was from an earlier equation we had. B is mu naught IN. And so if we bring back this equation, L is equal to N phi B over I, which capital N is just lowercase n times L. The flux is BA over I, and then we can kind of plug some things in here. And so we still have our NL, and then we're going to plug in for the magnetic field. It's mu naught I times N. Area is still just the area. And then all of this is over the current. Which we do get an interesting kind of a result that the current cancels out. Interesting. And so then we're going to rewrite it in terms of L over lowercase l. So that's the inductance per length. Right? And so that's equal to mu naught n squared times the area. And this is the inductance per length of a solenoid. Right. And the reason we do it as inductance per length is so the length of the solenoid doesn't matter. We're looking for something that, like, if I come along and say, okay, now the solenoid's twice as long, like, it doesn't matter. That's not one of the interesting characteristics of a solenoid. Right? The interesting characteristics are the area, how big it is, and then lowercase n, the amount of coils per length. And so how tightly you wind it and how big the area is. Right? And so very similarly to when we had what we had with capacitors, where we were able to find like a geometric, let's see, we had C was equal to epsilon naught, and then let's see, there's an area and a distance. As the distance gets bigger, capacitance gets smaller, so we had A over D, right? And so we had this expression that was a constant and then just some geometry. Now we have a constant and some geometry, right? And so that's what the goal was for this. Yeah, and so that's all fine. That's good. We're having a good time. Okay. Right, and so again, the tighter you wrap the coils, and the larger the area, the greater the inductance. Cool. Okay, and then let's go to 38. Self-inductant. Nope, no. It was close. Self-induction. Right, self-inductance, self-induction, whatever. Okay. Well, let's think about this. I'm gonna kind of stray from the book briefly. Let's say we have a potential. We'll put a resistor in there just 'cause it's always good to have a resistor. And then we have an inductor, right, or a solenoid. I feel like I could draw better. Okay, and so we have a current that's going to go this way. The wires are curling this way out of the page and then back into the page. And so we're going to get a magnetic field this way going through this, right? Just like the right-hand rule practice problems we do in class where it says, like, hey, here's a giant coil, current's going this way. What do we get for the magnetic field? Right, exact same thing. But I want you to imagine, let's who needs an imagination? Oh, that was too much. Yeah. So how do we want to do this? Get rid of this, and we'll say there's a switch, right? Okay, and so when the switch is open, okay, so we'll write things down. We're gonna think about the flux here. So phi sub b is equal to 0. And we'll say initially. Right? Initially, when the switch is open, the flux is equal to 0. Okay. And so then we come along and we close this switch. We get this. And now all of a sudden, current starts I guess we could have also said I is also equal to 0. Right. So then when the switch is closed, so when the switch is closed, a current begins to flow. Right, this current, I don't know, I'm going to make it a slightly different color. All right, and so once the current gets here, it's going to start traveling through these wires, as current does. And it's going to start going around these loops. And so as the current flows through the loops, it creates a B field. Right, nothing new, right? As the current flows through the loops, it creates a B field, just like the solenoid I used to pick up all the nails in class, right? But now we have a d phi dt, okay? And Lenz's law tells us so Faraday's law tells us we get an EMF negative d phi dt. Right, and then Lenz's law says, hey, this EMF, it's going to directly oppose everything you're doing. And so what do we get? We want to make, right, we said if the current's going through this way, we get a magnetic field going this way. And so in order to oppose that, we want to make a magnetic field going this way. And for that to happen, we need a current that travels this way. So you may see we are at an impasse. And so initially what happens, the moment you close the switch, you get an EMF that is equal and opposite to V, right? You get no current that flows the moment you shut the switch off. Okay. Because of Faraday and Lenz's law, right? The EMF you produce is going to be directly equal and opposite to the potential you applied. And so okay, and so no current flows. Okay, no current's flowing, so d phi dt is equal to 0, so the EMF goes to 0, so some current can flow. Right? And we get into a very cyclical pattern here of the EMF opposes equal and oppositely. It stops anything from happening. Nothing's happening, so there is no more induced EMF, and so something can happen, but then that something starts happening, and so what you get is it takes a long time for this to be able to get to its full current, right? So if we were to plot current as a function of time, crazy the book doesn't do this. Like, this seems like it would be a really good plot to have. It might be in the next section. I might be jumping ahead a little bit, but it's okay. Is it? Huh. Oh, it has potential as a function of time. Which... So let's see, what is... Nah, whatever. Alright, you're gonna end up with... Let me see. I believe you get something like this. Is that right? So let's see. I is equal to epsilon naught over r times 1 minus e to the negative t over tau. Yeah, this looks right. Right, because if it was just e to the negative t over tau, we'd have something like this. We get the opposite. Yeah. And we'll get into this equation later. We'll sanity check. Who knows? Maybe I'm insane. Right. And so this is what the current looks like as a function of time. And so the idea there being this is a constant applied potential, right? It's a battery, it's a power source, it is whatever. And so it is unrelenting, it is always going to be trying to move charge. That is what potentials do, right? It is just incentivizing things to move, just like gravity incentivizes things to fall. Exactly the same concepts. But Lenz's law and Faraday's law, they are reactionary, right? They only react to what is happening to them. And so they eventually lose out to the constant pressure the battery applies. But they go kicking and screaming, right? They put up a good fight. Good for them. Okay. And so we had for the inductor, all right, our flux linkage, we called it, was equal to the inductance times the current. And then Faraday's law tells us that the EMF is negative n phi b dt. Right, and I put the n inside here so we can kind of mimic what we have. And then so then we get the potential from a inductor and this is the self-induced EMF. Right, the whole idea behind self-induction is the coil here is making the magnetic field that it is then reacting to, right? So it creates a magnetic field which changes the flux through it, so it induces an EMF to oppose that, but the battery wears it down over time, and eventually, and so let's talk about it. So we can say through this circuit at t equals 0, I equals 0. If t equals 0 is when we shut the switch. And then at t is equal to infinity, I is equal to V over R. Right? That's the important thing to keep in mind for an RL circuit, which we're not fully into an RL circuit yet. Well, this is an RL circuit, but that's not the section we're covering. We're just worried about the self-induction. Similarly to how when we had a circuit with a resistor and a capacitor, it was at t equals 0, I is equal to V over R, and then at t equals infinity, I is equal to 0. Right? because once you have enough charge built up on these plates, you get a potential equal and opposite, and no current can flow. And so there you build up charge to get the potential. Here we are changing the flux to get a potential. And so you can see these are kind of, you know, the opposite cases of each other. And that's neat. Okay. And I think self-induction is where we're wrapping it up for today.